请大家注意，本演讲厅内禁止饮食。Please note that no food or drinks are allowed in this lecture room.
太小声是不是？那个板子呢？
板子，说那个平板吗？
对。
平板应该在那个女生那边。
哦，要调大声一点。人
应该在外面吧？在那边，在那边。我看讲话，可以吧？如果你觉得我太小声，就帮我调大声一点，可以吗？
他有没有写数字？
谢谢。
试一下音量。
喂，应该可以。我说如果音量不行的话，再请他帮我调。对，都可以。
有那个。
各位贵宾，大家好。如果等一下主持人上来，我就先下去嘛。
在旁边这样。
各位老师、各位贵宾，大家好，欢迎来到中正大学参加第61届中华民国数学会年会。Good morning, distinguished professors, participants, ladies and gentlemen. Welcome to National Chongqing University for the 61st annual meeting of the Taiwanese Mathematical Society. 首先，请中华民国数学学会理事长谢明伦教授为我们开场致辞。First, let us welcome the President of Taiwan Mathematical Society, Professor Min-Lun Xie, to give an opening remark.
Everyone, and this is the first annual meeting of Taiwan Mathematical Society, and I would like to thank the host, National Chongqing University, for their help and the local organization. So also, I would like to welcome our long-term friend Japan Mathematical Society. So Professor Ishige and the delegation from Japan Mathematical Society. So this year we our academic committee organized several sessions in mathematics, and I believe and I hope all of you will be able to enjoy the scientific activities and also the banquet tonight. And so please, all of you are welcome to attend our banquet. And so thank you very much, and I hope you enjoy your stay in Chiayi. Thank you.
谢谢理事长 ，Thank you, President 谢。接下来，请中正大学蔡少正校长为数学年会做开幕致辞。Next, we are honored to invite Professor Shao Zhen Cai, President of National Chongqing University, to deliver his opening address. President Cai, please.
Good morning, everyone. Welcome to National Chongqing University. I think this is the third time that the CCU hosts the annual conference of the Taiwan Mathematics Society. CCU is relatively young university. We established in 1989, but we are so brave to host the first Taiwan Mathematics Society annual meeting 6 years after the starting of our university. And then in 2009, we also host the annual meeting. So this will be the third time that National Chongqing University hosts this annual event. I understand that we have a distinguished guest from Japan, Philippines, and all other countries. Many of you maybe this is the first time that you visit CCU, but I think you need to understand that CCU is the most beautiful campus in Taiwan. In the drama series of the Material Garden, maybe some of you understand that. So once you are here, welcome to go to the scenic site and then take a selfie for yourself. So mathematics is the very dedicated science. All the mathematicians are very smart and they have a very clear logic thinking. Myself, I escaped from mathematics when I was 16 years old. Okay, so I go to study biology instead of mathematics. So later on, that I would welcome all of you to this annual event. As my understanding, we have 10 different topics. I think this is a very brainstorming get together event, because from the theoretical mathematics to applied mathematics.
We are now
I
starting
think
the
now
ceremony.
with
Opening
the
ceremony.
AI and also all the computing powers and also the big data, I think mathematics has become one of the most critical basic science, because all of these applied area, they all need the theory of mathematics and also need the modeling based on the mathematics. And I'm very pleased to share the new establishment of the National Zhongzheng University. Because of the AI, now we are praying to establish our Silicon Photonics College. And this Silicon Photonics is not only technical, it also needs a lot of computational power and modeling for those. So in CCU, now we try to merge the multi-discipline and together to push forward for the next century of the technology. So I'm very happy that so many of you gathering in this campus. So I wish every one of you have a very fruitful outcomes, and wish everyone to stay here and then take your time to walk around the campus and then have a very happy and also have a very successful meeting. Thank you very much.
谢谢蔡校长。Thank you, President Tsai. 接下来，我们欢迎中正大学理学院陈永恩院长为年会致开幕词。Next, please join me in welcoming Professor Michael Chen, Dean of the College of Science at National Zhongzheng University, to address us at this annual meeting.
President Tsai, President Xie, and then our honorable guest. Good morning, everyone, for coming to the National Zhongzheng University and also the 61st TMS annual meeting. So I would like to thank the organizer and also the Department of Mathematics of CCU for organizing this wonderful event. The Department of Mathematics is a very important department under the College of Science. It's not only because it's one of the largest department in CCU, but also because most of the students, I would say most of the students in CCU need to take freshman calculus. So it takes a very important jobs in the CCU. And of course, we know that mathematics is also a very important subject to link from science, engineering, and also different kinds of subjects. So as a biologist, same as President Tsai, I didn't study mathematics very well in my undergraduate. And because I think I won't be able to use mathematics in my future career. But when I went to the United States to have my postdoc training, I have the opportunity to work with mathematician and statistician and work under the Systems Biology Center. And then more interestingly, when I joined CCU almost 20 years ago, I told a group, the faculty from the Department of Mathematics that I have been working with mathematician before. And then somehow I know that I didn't know any mathematician. I didn't know any mathematics. So, but they keep asked me to collaborate with them. And then so in the past few years, and I did have several publications with the Department of Mathematics in terms of differential equations and also statistics. So in this case, I think I am the right person to deliver the opening address in the TMS meeting. And so I hope every one of you can enjoy this meeting and also the beautiful campus in CCU. And then don't remember to have a very tasty chicken rice of Jiayi. Okay, so I wish every success of the meeting. Thank you.
谢谢陈院长 ，Thank you, Dean Chen。感谢以上贵宾的致辞勉励与祝福。现在我们邀请谢明伦理事长介绍接下来的议程。We now invite President Min Lun Xie to introduce the following programs of the meeting.
So our first lecture is the plenary our plenary speaker by Professor Karanidia Dakis. Sorry, yeah, from Brown University. The chair of this of the plenary speech is Professor Hu Weifan. Yeah, so please.
Okay, good morning, everyone. This is Weifan Hu from National Central University. Yeah, and it is my great honor to welcome you to this plenary session, which will be held online. And today we are going to have privilege of hosting a highly distinguished scholar whose work had a profound impact on computational mathematics, scientific computing, and machine learning. I'm delighted to introduce Professor George Kaniadakis, who is currently a full professor of applied mathematics at Brown University. And he has previously held faculty positions at several leading institutions, including Princeton University, Caltech, and MIT. Professor Kaniadakis is a world-renowned applied mathematician known for his pioneering contributions to high-dimensional stochastic modeling and multi-scale simulations, and most recently, of course, AI and machine learning methods for partial differential equations. And his research not only advances the theoretical foundations of applied mathematics, but also plays a transformative role in shaping fixed-informed learning machine and deep nets. In particular, one of his papers published in Journal of Computational Physics so far has been cited over 20,000 times. So over his distinguished career, Professor Kaniadakis has been honored with numerous prestigious awards, such as SIAM ACM Prize in Computational Science and Engineering, and the inaugural J. Tinsley Oldham Medal from the US Association for Computational Mechanics. In addition, He's also a fellow of SIAM and the American Physical Society and the American Society of Mechanical Engineers. Yeah, so it is with my great pleasure that I invite Professor Kanadakis to deliver his lecture entitled by, so do I have the title page here? Oh, okay, thank you. Oh, 3 scenarios of physics-informed learning machines. So please join me in welcoming Professor Kanadakis. Oh, I'm sorry. I'm sorry. Yeah, sorry. Yeah, so the title is From Physics-Informed Machine Learning to Physics-Informed Machine Intelligence. And yeah, thank you.
Can you see my screen?
Yeah.
Okay, and you can hear me, right?
Yes. Okay. 这是哪一台坏？我这台吗？
Okay, I can start. All right. Thank you very much for inviting me here. Zhao Shanhao. I'm sorry I'm not there in person to exchange information on this topic, but I would like to talk about how machine learning is changing the landscape in science, in education, and also in mathematics. So we are at a critical point of mathematics where we already see big changes on how we conduct research in mathematics and how we educate our students. So Quo Vadimus, that I use here in red, Quo Vadimus is a Latin word for saying, where are we going? So today I hope to give you my point of view of how AI and deep learning in particular has changed the way we are thinking about solving mathematical problems, but also applications problems. So in fact, in applications, we usually have what we had so far is this schematic here, where we typically know all the physics of a problem. We know the PDE, we pretend we know the coefficients, the parameter range, the domain, everything. The problem is well posed, and then just need some more information on boundary conditions, initial conditions to solve the problem. Unfortunately, the real world is pretty much what I have here in the middle, where we know some of the physics, which we can model with PDEs, partial differential equations, partially, but a lot of the physics is also unknown. But you have some measurements. In the real world, you have measurements. Of course, in today's world, we have more and more measurements, more and more data. And the question is how we can combine in a seamless way the physics, which is, of course, described by mathematical equations, with the data. And the data, of course, could be noisy data. It doesn't have to be data where we need them to be, for example, at the boundaries. It could be random data, sparse data, sporadic data everywhere. So I will talk about that. Is my main topic, and that is what one will do in computational mathematics. There's also a case here, which I have on the right, where we have very complex systems for which it's impossible to write down the equations. But even if you can write them, you can really not solve them. It's intractable problems. In that case, we need something else, and I will talk about neural operators, a higher level of abstraction that I introduced a few years ago, which are changing the world and is appropriate for what the people are called digital twins. So here's the outline of my talk. The main part of my talk is scientific machine learning, which is an emerging field, which I started about 10 years ago. And within that, I will talk about physics-informed neural networks, or PINs, very popular method. And then, as I said, I will go to a higher level of abstraction with neural operators. The last part of my talk, I will discuss agentic scientific machine learning, how one can use multi-agents to generate hypotheses, test if the problems are well posed, and solve them with the best method that's available. So that's the true intelligence, and that's what we're benefiting now from AGI, artificial general intelligence, that is now spread also into mathematics. So if we take a look at the history of AI, it goes back to the 60s. And as you can see, somewhere here, there were ups and downs in the beginning, but somewhere here is where NVIDIA produced the hardware, the GPUs. And then, as you can see, we have a monotonic progress since then. I want to pay attention to transformers. Transformers has been actually AlphaGo, before we go that, to AlphaGo by DeepMind. So DeepMind makes its presence at that time. Transformers by Google, that changed totally the field on large language models. And as we go forward, AlphaFold, it's a huge breakthrough that was given the Nobel Prize last year in chemistry. And more recently, we have AlphaEvolve, which is agentic science using multi-agents to prove mathematical theorems. And in a more recent paper by world-famous mathematician Terry Tao, they solved 67 different mathematical problems, including very elaborate proofs, some of them with exhibited superhuman performance. So it's a complicated world. It's a fast-changing world, especially last year and this year. So I'm going to give you some flavor of that, the way we live it through development of new tools, but also through applications. So here's a history of deep learning. And I want to make the point that as far back as 1994, there was a paper by some chemical engineers who were trying to use neural networks to solve PDEs. Okay, at the time, of course, we didn't have the hardware and we didn't have all the algorithms that required for it. But in 2017, we introduced physics-informed neural networks, both for forward and inverse problems. And then I organized at Brown University, where I am, a scientific machine learning conference, the first of its kind. And then the Department of Energy came up with a report around the same time and so on. So you can see here, there's a hierarchy. You can think of artificial intelligence as a superset, and a subset is machine learning. Within neural networks is a subset, and then scientific machine learning is a subset of machine learning or neural networks. Okay, so I just want to start with this theorem that was proved back in 1993 by George Saipenko, an applied mathematician at Tufts University, where he showed that it's a very shallow, just a single layer neural network. These are here the neurons. Here's the input, and here's the output. So from left to right, we go from input to output. As you can see, we only have a single layer of neurons. And he said that this very simple construction, where we take a linear, so here's the weights, and we take a linear combination of these weights, W2 of the last layer, times some basis, and that basis sigma is a nonlinear function that takes as an argument this affine transformation of the input. W is the weights, B as the bias is, and X is the input. So basically, he proved that this is a universal approximation, function approximation, in a sense that the Y, the approximation, could be very close to a function f of x, which is continuous within epsilon distance, if sigma satisfies certain properties, as you can see here. and in the definition. So for example, in the neural network, you cannot have polynomials as we do have in all other numerical methods. Most numerical methods that we deal with, except Fourier methods, use polynomials as a basis. But in neural networks, we take a different path, and we take non-polynomials to approximate functions. And it says that this is a minimalistic approximation because even with the very shallow neural network, a single layer, I can approximate any complicated function. So that's the theory. However, in practice, it's very difficult to realize this. And in fact, today we know that there are some functions, I can construct functions, including discontinuous functions, which cannot be approximated by a shallow neural network. Instead, we use deep neural networks. So here again, I'm looking at a function of two arguments, x1 and x2. This is the input. Sigma, which I introduced earlier, is called the activation function. So use activation function in every layer. This is the first layer, second layer, third layer, and the last layer. So in every layer, you apply this function sigma, and recursively, you propagate the input from left to right. In the last layer, we don't impose the nonlinear function. Therefore, this weights of the last layer, this WIL, the last layer, I can use them to write again the approximation. So the neural network parameterized by theta. Theta here would basically denote the weights and the biases. Well, I can write my approximation of a function again, as before, as a linear combination of some bases. And in this form, you can think of Fourier expansions. I have some coefficients unknown times e to the I kx, that's my basis. But here, the basis phi corresponds to the functions that are generated dynamically as we take many iterations in the last nonlinear layer, in the last layer of the neural network where the activation function is applied. And then we have the output here. So in other words, what we saw for a single layer can be applied also to a deep neural network, but also it reminds us of finite element approximations or Fourier series expansions, where we approximate a function as a linear combination of some bases. The difference, of course, here is that this basis is not selected a priori, so we don't have exponentials, we don't have polynomials. It is computed on the fly, and it is changed dynamically, and that's why I call this adaptive basis viewpoint. Just to make the point of connecting neural networks with standard finite elements, for those of you who are exposed to that, in finite elements we use these basis functions, let's say linear, we call them the hat functions. But notice that in neural networks we use this sigma, these activation functions, which are like a ramp function, and we call them ReLU functions. These are ReLU functions. And notice that I can write phi of x exactly as a linear combination of these sigma functions. So therefore, there's an intimate connection between linear finite element basis phi and neural networks, because this phi spans the set of the ReLU functions that take a linear input x. Now this is in 1D, but it turns out it takes a little more time to do the proofs for higher dimensions. For D, D is the dimension of the space here. And the linear finite elements is not a subspace of a shallow neural network, but this is where we go to deep neural networks. And again, we can see exact equivalence, and there's some papers that show that. So this is just some preliminaries to show you that indeed these neural networks is really just like another numerical methods that allow us to do lots of commercial things like classification tasks, but also it allows us to do regression tasks, and therefore is a good candidate to solve partial differential equations. And this is how we introduced pins back 10 years ago in 2017 was the first, we put the 2 papers on the archive for solving forward and inverse problems. So again, what is a pin? Here is a neural network which I talked about again before. So I have x1 and x2, and in this particular case, I can have a vector u1 and u2. And let's say I'm trying to solve the momentum equation, the Navier equations for materials, for elasticity. Well, the mathematics of machine learning, of neural networks, is very simple. You're trying to predict u1 and u2, and you are given tokens or labels. Labels means you know the answer for u1 and u2 for x1 and x2, and you know it for 100 pairs or 1,000 pairs and so on. If that's the case, then basically you minimize the mean square error. It's just a least square fitting, and therefore from this minimization, you can go back and forth and iterate here. As you can see, you can find the connections, you can find the biases and the weights, which are basically the unknowns of this neural network. If you find the neural network, you know u1 and u2. The problem is you need a lot of measurements. You need typically you need to do experiments for it. So you need a lot of money to do experiments, even for a simple task of function approximation. Imagine when you try to solve PDE. So what we realize is that we're trying to solve a PDE. In this particular case, I want F1 and F2 to be 0. Again, this is the elasticity equation, sigma. You can think of sigma as stresses, and U1 and U2 are the displacement. But what we realize is that U1 and U2 are differentiable functions. Therefore, we can take derivatives of them. And if we take the differential operators, then you can form the equations, and you try to minimize these equations. And when you try to minimize these equations, basically, you have down here, yeah, oops, go back. You try to minimize this equation, so you penalize them, so you want those terms to be 0. So now you can have some data, you can have the physics. So this is the physics here, and this is the data. So you use the physics by computing these equations that you're trying to minimize, you're trying the residuals F1 and F2 to be 0. At different points, you basically don't need so many points. Or even if you don't have any data points at all, this term here will be 0, and then you're solving the equations forward. If you don't know the physics at all, then this term is 0, and the other term here is non-zero. So you solve the inverse problem. So you can solve the inverse problem, or you can solve the forward problem. Okay, so that's really the idea behind pins, and that has been used everywhere. For example, if you want to solve this Berger's equation, you can see here nonlinearity, you can see a second derivative in space, first derivative in time. This is x, and this is t. So here we don't have any data, we just have boundary conditions, initial conditions here. And then we have boundary conditions at x equals -1 and +1 is the domain. But notice that there are periods of time where we don't have initial boundary conditions at all. So this problem is ill-posed. So with the classical methods, with any classical method, we'll not be able to solve even this problem because of the lack of boundary conditions continuously in time. You cannot interpolate because this is very large distance. However, in the new setting, we don't have the issue of ill-posedness, and in fact, it's an optimization problem. And you can see a very short code here in TensorFlow now where you JAX, but very quickly in 10 minutes, even a high school student can solve this problem, something that takes us 1 semester. It took us 1 semester in class to teach our graduate students, our PhD students. So does this method converge? Yes, the answer is yes. We early on in 2020, we wrote a paper where we show that this method converges for parabolic equations and elliptic equations, linear. In fact, we show that we have existence of solutions even when the boundary conditions are not there in the L2 sense. But if we impose the boundary conditions, then we have stronger convergence in the H1 sense. We can also produce error bounds, as you can see here, using the functionals, and I will not bother you with that. Now, what happened since we first developed this method? we developed this method, the error versus the number of iterations, was this curve here. Yeah. Yes, sir. Yeah. What does it say? What does it pay? Can you read the title of the page so I can see it? Oh, you should have told me earlier, because I'm now on the 12 slide. Can you see my screen? Can you still see my screen? Can you see this changing now? Okay, so if I go to the full screen, can you see it now? Can you see it says the history of AI? This is now okay? Okay, so so here I talked about the universal approximation theorem. Did you see this page? Okay, tell me where did you see this one? Okay. So you can see now turning, right? Okay, here. Did you see this one or not? It says pins. What is a pin? Okay. Okay. So this is the pin. This is the pin, and it shows that we use physics here on the right. Okay. And then in addition to this term, which is the data, we also have this term, which is the physics. And then together, and we minimize that, and we find the network, which means we find the weights and the biases. In other words, a pin is an extension of a neural network where the physics is embedded, and all these differential operators are not approximate. They're exact because they are computed on what is called automatic differentiation using computational graphs. So the new technology is that we can compute derivatives exactly, and it's not required to do a grid. In fact, what we have here is random sampling in space, just like Monte Carlo. So you can think of sampling the space-time space-time domain. We sample it like Monte Carlo at random points to enforce the physics, and that's how we generate data. And of course, neural networks are hungry for data. Is this clear? Can somebody confirm that you can see? Okay. All right. So now this is an example. It worked well. Okay. Please stop immediately as when you don't see. So now moving to the next one that shows. The next one shows the convergence and generalization of physics-informed neural networks. It shows a paper from 2020 where we show that we for first time we show convergence of this method, and then in the next slide we show that we can compute also error estimates a priori for the continuous formulation where we sample at infinity. Of course, that's impractical. You always do it finite, but also okay. So now I was trying to say that 10 years later, what have we seen? Well, the method is still working fine, except when we started for this equation, the Berger's equation that I show, we plot the error versus the number of iterations. What we obtained 10 years ago was this curve, the green curve on the top, right? However, using new optimization methods, and optimization is the big problem in neural networks, not just for mathematics, but all neural networks. Now we're able to reduce the error down to here, down to machine accuracy. So, and we did that using new second-order optimizers, Newton-type methods, but a class that is called self-scale methods, methods which were developed in the optimization community in the 90s, but nobody has used it yet in neural networks. So we were the first to use it and reduce the errors of neural networks by many orders of magnitude. So it turns out that the method is exact. So doing this, we could solve very complex equations. For example, the Burgers equation, we went down to 10 to the minus 8. SOAP is another method developed by Google, which is also second order. But you can see here in this comparison that this is ours here, yeah, versus the Google. Google here is the middle. And you can see that we beat Google by 2 orders of magnitude or 1 order of magnitude and so on for all methods, including Gisborne-Landau PDEs and Kuramoto-Zhivazinski and the chaotic, and you can see here the solution. So anyway, this is very good method. I will skip this part here to show you how the method can be used to beat the Kirchhoff dimensionality. And we do that for equations like Hamilton-Jacobi-Bellman equations and also Fokker-Planck equations. So let's consider just for explaining the method, a Poisson equation in D dimensions, and D is very high. D could be 10 or 100 or 1,000 or even 100,000. Okay, how we can solve? Can we solve, very high dimensional equations? So we can see that this is what is called the loss function, the residual, and you try to penalize that. Then you treat the gradient of that, because the gradient of the residual with respect to the parameters of the neural network drives the whole process. If that is 0, then we're done. Okay, in the computation of that, you can see that we have the blue terms and we have the red terms. The red terms depend on theta, and theta are the parameters of the network. The blue terms that do not depend on theta, therefore we can pre-compute. So we can pre-compute the blue terms, and then to compute this term, which is very, very big, right? Imagine you have 1,000 dimensions in a big domain. It's not even possible to put it in the memory of a computer. So what we would do, we would take, instead of D, we'll take a subset of dimensions. Let's say we have 1,000 dimensions. Then we'll take 100 subsets of 10 dimensions each, and we'll try to do sampling of that. This is used, this is a concept in neural networks, is called mini batching. We do that for points where we sample. Now I want to sample the dimensionality of the problem. So this is what this algorithm basically say here, that you can choose random indices, which is a subset of the dimensionality, and then you can compute, and then you can sample by sampling, and you come up with an unbiased way of doing it to get good accuracy. So we have theory that basically shows that we call it a stochastic dimension gradient descent. Typically, people solve this with stochastic gradient descent, which, as I said, is really the main method in neural networks. But here we also take the dimensionality and we sample it, as I mentioned before, and then we show that we have convergence, and we also show that we can get good error estimate depending on the learning rate of the neural network. So here's an example that we beat the Kirchhoff dimensionality, and we're looking at the Hamilton-Jacobi-Bellman equation with this solution, which is not trivial. You can see the solution is not separable. And the state of the art using other neural networks, in fact, was some work from Peking University, where for 250 dimensions, they require 38 hours. And more recently, they improved it to 12 hours. And the accuracy was 10 to the minus 2. We only require 210 minutes, and the error is smaller, 10 to the minus 3. Now, if we go to 1,000 dimensions for the same equation, they require more than 5 days, and of course they don't converge. But we only require 7 minutes longer going from 250 to 1,000. So basically, it's the same time, right? Because just the memory takes a little time. And we still have a 10 to the minus 3 accuracy. And you can see here that I even have a result of 100,000 dimensions, takes 855 minutes, and the accuracy is pretty respectable, 0.4%, 4% accuracy. Okay, so this and other examples. In fact, we just wrote a review paper in SIAM Reviews in Education to show how neural networks and pins in particular, but also other methods, can really beat the Kirchhoff dimensionality. And that's something new compared to what we had before with other methods. There are applications also. We can combine this with hidden fluid mechanics, how you can solve multi-physics problems where you're only given visualizations. Can you actually compute a qualitative visualization into a quantitative form? This is something complicated that I cannot really explain, but basically they're giving you a video of flow visualization, which is we treat as a passive scalar. And then from that, you don't know anything about the Navier-Stokes equations. You don't know the domain. You don't know the parameters. You only assume that they are valid, but you don't have any measurements. And you are able, because you find the weights and the biases, it's a couple problem, from the visualization to solve the PDE, the Navier-Stokes PDEs on arbitrary domains, these flower cuts, cut like flowers domains, show that you can actually do it on arbitrary domains, as long as you know the passive scalar there. So we use that in medicine recently with a neuroscientist, and we're able to, from MRI, only images of MRI, we're able, and this is shown a live mouse, we inject some tracer in the brain of the mouse, and then we've, just from the tracer of the, where the tracer goes, basically diffuses and transported through the permeable walls of the brain, everywhere in the brain. There's a fluid where our brain is sitting, it's called CSF fluid. We're able to detect, to solve basically the flow equations from these dyes, just using the data. The only data that are given is this visualization. And in fact, here you can see in this movie, I hope you see a movie, it's the entire brain of the mouse, of a live mouse, turning. And red is high speed, high velocity, blue is low velocity, and yellow is in between. So basically, we are able to infer, for first time ever, the 3D velocity in a live mouse. And hopefully this soon will be done for people. So there are lots of diseases associated with this, for example, Parkinson and Alzheimer's. So pins have been a huge success in industry. I work with Toyota, GE Aerospace, Hitachi, Bosch, Siemens, and many big companies. The first person to adopt in industry was Jensen Huang, who I think his roots are from Taiwan, if I'm not mistaken. He's the CEO of NVIDIA. So he basically hired my postdoc, Marja Raisi, to start this in NVIDIA. And now they have they simulate the Earth climate and very big applications. I asked ChatGPT and DALL-E to tell me what areas pins are used, and used basically everywhere, because from financial mathematics to environment to autonomous systems, renewable energy, climate, and so on. And more recently, you may have seen this paper by collaboration between DeepMind and Stanford, some faculty. In fact, the professor from Stanford, Qinlai Yao, is from Taiwan, I think. They work together, and they produce a very high precision pins version in order to discover if the Navier-Stokes equations have singularities. And for first time ever, they were able to show these singularities using pins, directly pins. And of course, this is one of the open problems, the $1 million question. So they may get the prize. So far I talked about all these great successes, but there was a paper a few years ago from MIT that discussed also the limitations. And one of the main limitations, you may already know, because all the countries in the world right now are trying to build energy centers. Why do you need energy centers to use neural networks? The answer is because they consume a lot of energy. So for us, we try to do mathematics and solve PDEs and so on. We don't want to spend a lot of energy. So we want to use smart algorithms to overcome that energy barrier. So just to show you how much energy is required, this is training of GPT-2. It requires more than air travel from New York City to San Francisco, which takes about 6 hours of air travel. And here, instead of the cost, I have the footprint of the CO2 emissions to see how bad it is. Of course, we're now ChatGPT 5.2, which requires probably 100 or 1,000 times more energy to train it. So, as I said, we want to develop new algorithms, and we went back to deconstruct the brain. And if you look at the brain, a lot of the activity is actually stochastic. So stochasticity prevails. And then if you look at the inputs are spikes. They're not continuous functions. Also, the memory is right there where the processor is, where the neurons are. So there's a very different architecture. So if you look at the human neuron, basically, you have the branches where the input comes, you have the soma where the computation is done, and you have the synaptic output. And the inputs are, as I said, these spikes like this. So voltage spikes. So we want to mimic that, because, as I said, just to recognize if with neural networks, if we have a cat or a dog, you need 250 watts. But for us, if we just have a good meal, we have, let's say, with 20 watts of energy, our human brain can think, you can sing, you can write poems, you can do math problems, and you can walk at the same time. So this multifunction is unique to human brain. And can we learn something from that? So that's sort of the idea. So we propose using, instead of continuous functions as input, we propose to use spiking neural networks, where the inputs will be similar to the human neuron. We call those spiking neural networks. Typically, so the spiking neural networks will go through the human neuron, through the membrane, and then depending on the voltage, if it exceeds a certain threshold, it will fire. So you don't fire all the time if there's no reason, if there's no meaning. So that's sort of the new idea, to develop methods and mathematics for spiking neural networks. If we can do that, you can see here the consumption of electricity will go down this way using algorithms, not just building more energy factories. So again, inspired by the human neuron, we developed the neural operator, where the inputs are functions and the outputs are also functions. So you see, a neural network takes as input data, and the output is data. But the neural operator is a high level of abstraction, okay? And in fact, the way we constructed this will be the branch, we call it branch, because that's the input. So this is associated with the input. And this here is associated with the soma, or what is called the trunk. This is where the basis, remember I talked earlier in my first slide about the basis. This is where the basis is produced so that we can express the operator in terms of this basis. Now, operators could be a PDE, it could be an integral, it could be a Laplace transform, it could be any mathematical operation. It could be an operator where it takes inputs as functions and the output is a function. Why is this good? Well, because instead of solving the PDE for one time, for one condition, we will train the neural network to solve PDEs for all possible boundary conditions, for many different domains, for many different parameters, all at once. So we don't have to retrain again and again. We just have to produce the answer. So what I'm talking about here is something fundamentally different. So this is standard neural network go from a finite dimensional space to another finite dimensional space. I'm talking about take a Banach space to another Banach space. Okay, so the inputs are functions, as I said, the outputs are functions. So we prove a universal approximation theorem for operators, thanks to for deep neural networks, because we found some work that Professor Chen from the University of Fudan in Shanghai had published back in 1993, and nobody ever paid attention to it. But we extended his theorem to neural networks, and basically says that the operator G that takes an input to the output, they will take an input U, the function, and give you an output G of U of Y, which is a function, can be approximated by a double sum of this form. And if you look carefully, this is a neural network, and this is another neural network. And basically, what I have is a sum of some coefficients B, K, phi, K, and phi K is like this. So again, I expand the entire operator using these coefficients, which I compute from the input function that I sample at some points, and then times a basis, and the second network that I have, just like the trunk or the soma in the human neuron compute. So inspired by that, so this is the simplification of that for a shallow neural network is like this, and we published this work in Nature Machine Intelligence 5 years ago. So we have the error analysis. I will not bother you with that. But one of the things that we also showed in a long paper with Sid Mishra from ETH, 100 pages paper, we show that the deep nets can break the Kirchhoff dimensionality in approximating general nonlinear operators. Also, the operators don't even have to be continuous. And we also remove the assumption of compactness. Now, how do you train this? We used to train it, the first time we train it simultaneously, but it turns out since you have the data, the functions, and the outputs, the tokens, you can first train the trunk only and compute the basis. After you compute the basis, you can do a QR decomposition to orthogonalize it, and then you can go back and use that basis to solve for the branch. So it's a 1-2 in 2 steps. And by doing that, you can solve very difficult problems. For example, here I show you how we can solve the so-called SOD or LAX problem in high-speed aerodynamics in Euler, compressible Euler equations, where the variable here is the pressure. So instead of solving for one pressure, you're solving for very large pressures for let's say from ratio of 10 to ratio of 10 billion. So now the neural operator is trained offline, and then online you can compute these solutions very accurately for any pressure that you specify in less than a microsecond. But of course, it takes hours to train it. But after you train this neural operator, it's like a ChatGPT. It's like ChatGPT for solving conservation laws. Okay, and it turns out that the reason this is successful because the basis we produce has this type of features where it looks like a local Fourier series or a wavelet, but then it also, even the 120 mode, it preserves the constant state. So you can see here one high mode of the basis for the operator. It looks like a Fourier series, but at this point is actually constant. And then it also has an oscillation. So we produce unique basis to express this operator that no other method can do. And that's and of course, this DeepONet is not, you can have graph neural networks, and you can have spiking neural networks for the branch net, and you can do the same thing for the trunk net. In other words, you can plug and play any type of architecture, neural architecture you have. So I direct a big center of Department of Energy. A lot of mathematicians from Caltech, Stanford are involved, including the national labs. And as you can see here, we focus on neural operators, graph neural networks, and spiking neural networks. And I already told you about the utility of spiking neural networks, but I want to elaborate a little more here to show you that this is what happens in human neurons. There's a voltage come in. When you exceed a certain threshold, then there's a firing. If you don't exceed it, there's no firing. Now, in artificial neural networks, what we do, we use activation functions. The sigma function that I told you about says, okay, I'm not going to bother with the details. I'm just going to have an ad hoc function. But now, as I said, we want to restore this. We want to go back to a human brain, and we want to say, okay, no more artificial neurons. We want real human neuron activity. So, of course, that brings a lot of questions. How you train it, how you take gradients, because these are not differentiable, and so on. But there are new hardware here on the top. I show the what's called by Intel, was produced by Intel, a very small chip that is called neuromorphic computers, called OIHI2. So we use that to build. So in this particular case, my branch is a full neural network, but my trunk is actually a spiking neural network. You can see the spikes coming in. So I can combine them and solve the Poisson equation. Unfortunately, the answer is not very good. Here, different solutions here for different inputs. As I said, I solved the Poisson equation for many different instances, but you can see the solution is like this staircase. If you sample it, if you encode it better, you can get a better solution, but you never get a good solution using this. The reason is because we use something called LIF, a leak and integrate and fire. It's a simple neuron model, and so this is what I was talking about. That gives you this. So this is what is used exclusively for spiking neural networks. But recently we upgraded the linear dependence, the linear PDE here, ODE for voltage, to a quadratic, as you can see here. And this quadratic changes totally everything. The spikes. So this is a classical human neuron model, the simplest of the models for human neurons. And now we introduce something different, which is actually differentiable. And you can see here's a spike, and here's also a spike. So now we solve the PDEs like the Berger's equation I showed you before. You can see the red lines correspond to a LIF model for the human neuron, but then the solid line, which is very close to the exact solution at different times, shows the QIF. So from going from LIF to QIF, we now have differentiable spiking neural networks, which makes a big difference because this type will be 100 times faster. Therefore, we consume 100 times less energy than artificial neural networks. There are all those sort of types of machine learning that I don't want to bother you about, but one of the things that we do is, of course, what happens if you learn to solve PDEs in these domains, and then you transfer it to different domains. And in fact, you can do that by modifying the loss functions, or if you have here elasticity equations from one domain to the other, or what happens if you train a neural network for this dynamical system. It's called the Brusselator diffusion reaction system. You train the system at the limit cycle. Can you actually predict, go through the bifurcation and predict a stationary point? The answer is yes, but you need. There's another paper we published in Nature Machine Intelligence. And you need to change your loss function to account for the difference between the distributions, the target distributions, and the source distribution. There's some interesting mathematics actually, which have to do with Hilbert spaces, but I don't have time to skip it. So currently, what is the state of the art is that we want to do this multitasking, right? Solve different equations. And there was a paper by Google, it's called Gato, for a cat. This cat, it appears, I think, in a science paper a couple of years ago. This cat could do 600 different tasks, could solve mathematics, but can also do poems and so on. So can we do that in mathematics? Can we learn neural operators that can solve different equations? For example, the Fisher equation here in different forms. And can we do it in different domains? And the answer is yes. Using transfer learning techniques and other methods, one can train a network on some differential equations, and then you can transfer that knowledge to other differential equations and also other domains that you have not seen before, and you may not have seen this equation before, but now you can solve it. And this is now I want to go to the last part of my talk. I'm almost done. A couple of more slides. And basically, I want to talk about what I told you so far requires a lot of manpower. You need to have lots of postdocs, lots of students. I have 30 students and postdocs in my lab who all do the same thing. But recently, using the LLMs, the large language models, which become smarter and smarter, and we have many of them, one can build agents. So in this last part, it's called agentic machine learning. What you see here, you only see one user. Every one of these other icons are not a real PhD student or not a real postdoc. It's really an avatar. Okay, so you can see we have two avatars, two agents working together to answer the question of the user. And basically, what they do is they decide how would they approach the question. And what's the question? Is it something that we can store? Or is it something that I can use with classical methods of scientific computing in the top? Or is it something that we can use using machine learning and scientific machine learning, as I told you? Then that's team A, then we go to team B. Team B, as you can see, is the retriever, the validator, the librarian. These are all the people who have access to thousands of papers and books. All my books are already there and so on. So these are agents. They can read 100,000 papers in a day and more, actually. So these are people who have the knowledge graph, not people, but avatars, agents. And then we go to the planner, exactly what the method to use. And then after you have a method, you want to implement it using a programmer. Here we use Claude. So all these avatars are basically different LLMs. And then you can see me down here. I'm an avatar. Even the advisor became an avatar. We don't need advisors anymore. And here's my colleague, a little older than me. And we call this Athena, Athena framework. Now, we ask Athena. Athena stands for Agentic Team for Hierarchical Evolutionary Numerical Algorithms. Athena, of course, was also a goddess in Greece, the goddess of wisdom and reasoning, and it's all about reasoning. So we asked ChatGPT to solve a 2D implicit Berger's equation with periodic boundary conditions. And of course, you could solve it using Fourier methods, could solve it with finite elements and so on, but it chose to solve it analytically. How did it solve analytically a 2D Berger's equation, which is nonlinear? Well, it observed that it's a periodic boundary conditions, and then it did a transform along the propagation direction. So he made that 1D, and then he used the method of characteristic and solved the problem exactly up to the point where the characteristics intersect, and then after that. So basically, it did something that a human would not do, because a human, for that problem, for example, for 30 years, I've been solving this using spectral methods instead. Okay, so then another case, we solved this flow problem where we said that you have some real measurements, these are the points, and there's the square domain, there's the flow, you drive the flow from the upper boundary with a Dirichlet boundary condition, and it forms a vortex like this. Okay, so how but we don't know the Reynolds number, we don't know the parameters, we don't know. So what Athena did is to first use pins to solve the inverse problems, because it turns out that pins are very, very good for inverse problems. So it solves all the inverse problems. It finds the Reynolds number, for example, the parameters, and also finds the field. Now that it knows the Reynolds number, it goes uses a finite element solution to smooth out the noisy field. So basically, in this particular example, it used both scientific machine learning and scientific computing, classical methods. It combined to get the best answer. Something, again, that is beyond human, so you can see superhuman performance. Anyway, that's where we are now. Of course, the agents are the ones who will choose the neural architectures. They choose all the parameters, all the fine-tuning. They will write the code. They will debug the code. And basically, you don't need any of the students or postdocs, except the creative ones maybe in the lab. So this is where we are now. 2025 and 2026 is the year of agents, and you can see that even in mathematics, and I already mentioned the paper by Terence Tao on pure mathematics, where they solved 67 problems that could not be solved before. So I would like to make some acknowledgements from my collaborators from Caltech and Stanford who work with me on this big project. It's a big multi-university project. And also I already mentioned the other Department of Energy project that supports my work. And this is the end. Thank you very much for listening. I hope you you could hear my talk and you could see also the slides. And I'm sorry about the problems earlier. I'm happy to answer questions.
Yeah, thank you, Professor Kanotakis, for the insightful and inspiring lecture. So we now have some time for questions and discussion. So any questions from our audience? Okay, so yeah, I do have one question. You just mentioned that you can solve a very high dimensional problem. Could you say more about the algorithm, about the stochastic high dimension?
I'm sorry, I cannot hear you at all.
You cannot hear me?
No, I cannot. Maybe come closer to it and stay steady. Yep.
Okay, so are we still steady now?
Yeah, a little steadier. Yeah.
Oh, okay. Yeah. Yeah, you just introduced us that you can solve the very high dimensional PDEs by
Yes.
Yeah. Could you say more about that algorithm? Can you hear me?
You mentioned that yes, I can solve high dimensional PDEs. I show the example for but it can be also nonlinear PDEs in the publication. We have shown this is Hamilton-Jacobi, which is of course nonlinear. But what is exactly the question?
I mean, could you show the algorithm for how do you solve it?
Oh, the algorithm.
Yeah.
Yeah, sure. So the algorithm is still a pins. It's like pins, but the difference is that so you see here. Here's the loss function. I hope you can see my screen. The loss function. So this is in this case. I just show the method for a high dimensional Poisson equation, right? But actually the results are for Hamilton-Jacobi-Bellman. So the key idea, maybe I can go to here. So the key idea is to choose random indices. If you see here, NL is the dimension, okay? So you choose random indices where I is the cardinality of a subset. And then for each subset, you solve these equations, and then you take a sum of all these. So you compute the unbiased stochastic gradient use this. So, but otherwise, all the derivatives are done with automatic differentiation, just like pins. So this is pins in high dimension. The new idea here is that we use stochasticity to look at to focus on some dimensions at a time, then other dimensions and other dimensions, and you have to do it carefully so that you don't introduce bias. So then in this theorem, we show that indeed this method, the stochastic dimensional gradient descent, is an unbiased method. So there's a proof of the theorem in our papers on that. Did I answer your question?
Sure. Yeah, I think due to time, there's one more question.
So thank you very much for the very interesting and insightful.
Sorry, I cannot hear you at all.
Okay, so thank you very much for the very interesting and insightful talk. So since you talk about the comparison of energy consumption, so and you also show us the spiking neural network. So say, for example, if we do a very big test by other neural network, and how does it compare? I mean, for the energy consumption with the energy that you used by spiking neural network.
Right. So in terms of the problem right now is that the SNNs are not very good on GPUs. So you have to compute them on specialized hardware. But if you look at the algorithmic complexity, if we estimate the algorithmic complexity is, and the memory, both memory and speed, is 100 to 1,000 times faster than other neural networks. So it's huge. You can see the memory, it's only 1% because you basically have spikes that you store. And then the computation, because of that, also the computational work is much, much less. And so, but the problem right now is that most of the neural networks are computed on GPUs. GPUs are very good in doing matrix vector multiplies, but they're not very good in other, for example, I cannot do sampling. If anybody has done Monte Carlo sampling on GPU, it's slower, much slower than CPUs. So what we need is a special soft hardware like Loihi that I show you. There's another one in Europe. It's called Spinnaker 2, which we work with these people now to implement. So in other words, these algorithms are there. The computational complexity is orders of magnitude lower than the artificial neural networks, but we don't have hardware to implement the proper hardware to implement them yet. I hope I answer your question.
Yeah, thank you very much.
Of course.
So is there any other question?
So can you hear me?
Now I can hear you, yes.
Okay, so in your last page of the slides, you mentioned causal inference in the last step, right? So I wonder that, so what kind of performance under your model can achieve the causal inference?
So which slide you said?
In the last page of your slides.
This is the last page.
No. So maybe the very, very last page.
This is the last
here.
page.
Yeah, here. So there's a causal inference on your slides, right?
So this is just a schematic of the center we have for the Department of Energy.
Yeah. So I'm curious that do you expect that your model can perform some kind of causal inference, maybe a little bit?
Perform? Sorry, I didn't hear the word perform.
Perform some part of the causal inference.
Causal inference. Oh, I see. Because I put here causal inference. Yes. So part. That's right. So the LLMs have that aspect, but part of the of our center is to develop models for causal inference. So that's why I have it here. I didn't talk about explicitly. I didn't talk about causal inference in here, but it's part of the center. This Department of Energy Center. That if you Google this word, you will get to this, and you can find. So that's something that is ongoing, and it's basically research. It's not implemented in algorithms yet. But these are the topics. These are the cross-cutting. These are sort of the areas, and these are the cross-cutting topics that we deal with: mathematics of machine learning, uncertainty quantification and trustworthy AI and causal inference is one of the main topics that that we are dealing in the center. Yeah. But I didn't say anything explicitly about that here.
Oh, that's fine. Thank you so much.
Yeah.
I think we are running out of time, so so I think we should stop here. Let's thanks Professor Kaniotrakis again.
Thank you very much. Thanks for your attention.
Thank you.
And have a good conference.
感谢各位嘉宾莅临参加第61届数学年会开幕仪式及聆听精彩生动的大会主讲。接下来是与会来宾一起大合照，请各位嘉宾以及来宾往中间位置移动。Thank you all for attending the opening ceremony of the 61st TMS annual meeting and for joining us for an inspiring plenary lecture. We will now proceed with a group photo. May we kindly invite all honored guests and participants to move towards the center of the room.不会讲，楼梯是可以站的哦，后面楼梯是可以站的。
站在上面可以往楼梯这边往前一点。
好，请大家看镜头，然后请微笑。Please look at the camera and smile. 1、2、3。那请比个赞 ，Give us a thumb up. 1、2、3。好，然后请大家单手秀一个数字，1到5都可以。Please show a number from 1 to 5 with one hand. 1、2、3。好，感谢大家的合作，使我们有美好的团体照。现在请各位嘉宾移驾至中庭领取餐点。哦。中庭4个角落皆可领取，并至2楼各研讨室用餐。学院邀请嘉宾们请至报道处旁边的贵宾休息室用餐，请大家注意，本演讲厅内禁止饮食。Thank you all for your cooperation. Please proceed outside to collect your lunch. Meals are available at all four corners. And please have lunch in the rooms on the second floor. Distinguished guests are invited to have lunch in the VIP lounge next to the registration desk. Please note that no food or drinks are allowed in this lecture room. 另外，下午的 Keynote Talks 将于1点开始，在 R106 与 R211 两个场地，请大家注意时间。尚未报到的贵宾，请至报到处完成报到手续，谢谢。然后申请交通补助的同学，请明天中午至现场注册柜台找王小姐。The afternoon keynote talks will begin at 1 p.m. in rooms R106 and R211. Guests who have not yet registered, please proceed to registration desk. Thank you.
The recording has stopped.
It works.
Test 1, 2, 3. Okay.